Thank you for being in the room. I know it's very exciting outside and there's daylight and coffee and conversation, all those things. However, this is going to be a wonderful session. It's going to be led by Joshua Rasera, who we heard speak yesterday from Imperial. And it's entitled Engineering the Lunar Surface, Regolith and Infrastructure. We have one fewer speaker, but we heard him yesterday. So Douglas Morrison, he can't speak today, but he did speak yesterday. And of course, I mean, I'm very glad you're here, but just in case anybody feels they're in the wrong room, the business pitches, robotics, satellites and energy is led by Larry Kutchko from ESRIC, and that's in the delegates room. It's running in parallel to this session here. And so I hope you enjoyed the session. I would continue to encourage people to sit closer to the front because yes, the lights are strong, but we really want, if there are fewer people in the room, to sit closer so that the speakers can see you as well, and it's easier for the Q&A afterwards. And there'll be a bit of flexibility in the Q&A because Douglas is not speaking. And thank you for those who are still watching online. I know that there's been feedback from those of you watching online, and we're very, very grateful for that too. It's really wonderful to have you still with us online for all of these extremely interesting talks. So with that, I hand over to Joshua.
Thank you so much for the introduction, Lisa. So welcome all to this plenary session on engineering the lunar surface, a regolith, and infrastructure. I think we have a very broad selection of talks today that all seem very, very interesting, and I can't wait to hear what we've got in store. So without further ado, I'd like to invite up our first speaker of the day, Alice Dottori from Politecnico di Milano, who will be talking about granular modeling of regolith plant interactions on for lunar ISRU applications. So without further ado.
So thank you, Joshua, and good morning, everybody. It's a pleasure to be here. So I'm gonna talk about a discrete element model of the lunar and small body regolith we are developing in Politecnico di Milano. But before diving into it, a bit of context and motivation on why we are developing such a model. So as you may have heard from the talk by Francesco on Monday, we are working together with the Italian Space Agency towards the demonstration on the lunar surface of the solid gas carbothermal reduction of regolith. And we are also, within the project, we are performing a preliminary design of the carbothermal plant. So we are quite interested in modeling and assessing the interaction of the regolith with different plant components, as well as we are involved in other feasibility study for surface exploration mission. So the interaction of the regolith with different components, it's a really key topic for us. And so for what regard the carbothermal plant, we actually won't need so many different processing stages for the regolith because from the experimental results we are actually having in those months, the process is quite agnostic with respect to regolith composition, meaning that for demonstration purpose at least, we are able to extract oxygen in the form of carbon oxide no matter what the composition. Obviously, if we are working with batches richer in iron oxide, the yield, the oxygen extraction yield is much higher, but we are able to extract some CO no matter what the composition. So we won't need a beneficiation stage in our plant. And as well as we won't need a grain dimension control stage for processes purposes because as you could see from the plot at the bottom, we tested different particle size distribution for our process and the outputs were quite similar. So we will need a grain dimension control stage just to avoid any risk of obstruction of our plant. So this is a very preliminary configuration idea of the lunar plant. And in red, there is the whole regolith handling unit that will manage the regolith up to the loading inside the reactor. And okay, so we were interested to, as I was saying before, study the interaction of all those components with the regolith, and for this we developed this discrete element model based on the C++ DEM engine library, together with the Chrono library. That it already implements a classic Earth-Mindlin mechanical model, to which we added a thermal and electrostatic model. So the code has two main parts. One in the one in C++, with which we control the simulation. We import the external object, we define the regolith properties, and we actually carry on the simulation. And the fourth part, that is the one highlighted in blue in the scheme, that is written, that is in CUDA, in a host, external host, and there we implemented the electrostatic force model and the thermal model, modeling conduction and radiation between the different particles. The two parts of the code interact through what they call wildcards, that are actually our property assigned to each clamp of a sphere that represent a regolith grain. And they are the typical properties we are interested in, so the position of each particle, their velocity components, their rotational status. And we added the one interesting for us for those kind of models, so we added the temperature information and the information on the charge status for each clamp. Then another big part of the work, of the initial work, was the definition of a pre-processing stage for the electrostatic model, in which we studied the different charging sources on the lunar regolith. So we defined different conditions depending on the illumination. So if we are in daylight or not, what kind of sources are acting for charging the regolith, and until which depth. So we are able to define different charges depending on the depth of our regolith batch we want to represent. So we run this pre-processing stage. We get the temperature and charge information that we can then apply to the complete model. Yeah, this is just a flow of the setup of the simulation, but looking at already some results. So we have this initial phase in which we define the grain properties. So we are able to represent different shapes for the clamps, composed by up to 6 spheres, positioned or in a triangular or more chaotic way. We can impose several radius to mimic whatever particle size distribution we are interested in. And we can apply up to 6 different materials to each clamp to mimic also the regolith composition. Once you have done that, we can generate the regolith batch layer by layer, as you can see at the beginning of the animation. And at that point, we applied the temperature and charge information to each layer, so to mimic the depth behavior, and taking into consideration also the material and physical property of each grain. Then we let all the simulation of the particle collapse, and we can go through a compactation stage to achieve the desired bulk density for our batch. And after that, we can import the external object, to which we apply the same electrostatic and thermal properties, and then carry on the simulation. So very briefly, I can show you some of the results we are getting, starting from a drilling simulation. So we have, for this case, we have generated a complete batch up to the compactation to get our desired bulk density for the regolith. We imported an external drill tip, to which we apply the desired charge depending on the condition we were simulating. And then we carried on the simulation varying different parameters, such as the vertical translation velocity and the rotational one. And we were interested in reconstructing the force exchanged by the drill tip and the regolith that we are able to with this model. And what is interesting is that we can separate the effect of the mechanical force, so coming from the Earth Mindling model, and the electrostatic one. And this information is useful to refine the design of the drill tip, but also well, looking into the conveyance of the regolith inside the drill. So we perform other conveyance simulation with the same model, with the same properties, to see if we are actually able to collect some of this regolith. And in this case, we were also interested in another outputs that we can get for this model, that is the contact information. So we are able to reconstruct contact that you see in red between each particle and the external object, but also the contact between the different particles. And we have some information about that, such as the duration of the contact. And so this is also interesting to refine the design of this such type of object. Then, going back a bit more on the ESRIC plant, we start simulating some sieving stages, so to control, as I was mentioning before, to control the dimension of the regolith particles we are loading. In this case, we were not able to import an external object due to computational power, so we represent the sieve as a clamp sphere with the same properties that we would have with a classical external object, and study the vibration of the best vibration strategy to achieve our results. And finally, we also perform a simulation of the loading of the regolith inside our reactor that is represented as an hollow cylinder to study the positioning of the different grains inside it in lunar gravity, and this kind of information. Very, very briefly, we also applied a similar model in using a proprietary software to couple those kind of simulation with CFD ones to study the fluidization of the bed, because we are working with fixed bed reactors, so we want to study the different condition in lunar gravity. That's all. So the model is working. We are refining it day by day, adding different features and try to optimize it. But we already had some result that we used to refine the design of our plant. So thank you for your attention. And if you have any question, I'm open to it.
Thank you very much for that. That was excellent. So I'd like to open the floor to questions, please. Yes, up front.
Thank you. Jakub Ciążela, Mirrorless Mining Data Services. My question is about temperatures, and specifically about night temperatures. I'm not sure what latitudes did you assume, but maybe you could try also lower temperatures, as in high latitudes they could be down even to 20 or 50 kelvins. So I'm wondering how it would work in those lower night temperatures. Thank you.
Thank you for the question. I mean, for what regard the model, we can impose whatever temperature we like. So we have an input vector, basically, for the temperature. We stuck to equatorial case as a baseline, but for sure we can make more simulation on that.
Thank you very much.
Any other questions? I have a question. Have you considered triboelectrification, tribocharging in your model, especially for sieving, because that I would imagine is quite problematic?
Not still, but it's an open point, to improve.
Perfect.
One more question here from Wupe. Wupe with Polymac. I would like to know if you are able to conduct wear analysis on your drill as you are drilling through the regolith, and would want to know the results concerning that. And the other thing is, I saw you use the outer EDM. what were the properties of the coefficient of restitution on your model? Thank you.
Okay, thank you. Yeah, for the first question, we were quite, let's say, limited in terms of computational power, so we have a small batch and we cannot go into that kind of analysis for now. So we try to have a dimension of the batch to avoid boundary effects, but no more than that for now. For sure is another thing we can work on. And for our entire ADAM, we use the same properties, so we actually span the coefficient of restitution from like 0.3 up to 0.7, if I remember well, for different simulation. Okay.
Any final questions? No? Well, please join me again. Oh, sorry, one more. Yes?
In your simulation, do I simulate actually the particles being irregular, highly elliptical in shape, or it's all spherical?
They are the particles are spherical, but they are made up in different clumps that I showed at the beginning. So they have a triangular shape or like a big spherical central. A big central sphere with smaller sphere around. So
okay, so you take into account.
Yeah.
Okay, thank you.
Great. Well, thank you very much.
Thank you.
Please join me in thanking Alice once more time. All right. Our next speaker is Damian Pietrusiak, who will be talking to us about Regolith simulant tests for discrete element simulation calibrations. Please.
Morning, everyone. Thank you for this kind introduction. And thank for the first presentation, because I think partially my presentation may give you some overview of how to approach the discrete element modeling, like how to find the coefficient of restitution and other parameters that are needed to have to be sure that the simulation is actually valid. So I represent Wroclaw University of Technology, and we have a bigger team, but we have also a colleague from Wrocław White Raven Academy, who is a great specialist in area of design of experiment. Okay, at the beginning, calibration needed. Why the calibration is needed, then main factors and measures, then design of experiment and potential application. So, as there were questions already, as there was a presentation, we would like to have simulation which is valid, so simulation accuracy. But on the other hand, that is the computational restriction, that if we simulate, if we would like to simulate, for example, I don't know, coconuts, probably that wouldn't be a problem because they are so big. So in the interaction with the interface of some equipment, the relative size is not that big change, and there is no many particles. But if we think about some powders, regolith, and that stuff, that's becoming to be a big computational challenge. And the question is what we are targeting. If we are targeting small laboratory scale tests, or medium, or large, or extra large. Sorry. Which in our case, as I show you, is more like large application, or maybe even extra large. So if we consider particles of regolith, which are more or less that size, and we assume that I would like to have my batch of simulation 1 centimeter square, I can even expect about some milliard of particles. But if I think about the excavation process of kilograms, it's becoming an enormous number. What would be the computational time? I don't know. It depends on the machine, but it depends also on the shape and many, many other parameters. So the question is how to have valid simulation, but on the other hand, how to have simulation which will fulfill the requirements of accuracy of our material. So the one thing is the size, and the other thing is, that was also the question, was the shape. So if we think about the regolith, we have on the left side presented samples simulant, and on the right side we have some samples from Apollo. And if we check more or less where we are on the basic chart of the roundness and sphericity, we are exactly in this place where it is marked. And of course, it will be the best to be on the top right, 0.9, where you have super sphere. It's easier to compute. We can have just less power, a faster simulation. However, it's good to try to find some trait, and I'm checking my simulation at more or less those three types, which is shape 0.1 is, of course, that top right, and the shape 0.3 is not exactly in the range which is marked, but I believe it's roughly about 0.7 to 0.7. So if we change in our simulation size, if we change in our simulation shape, how we can check if we have actually valid simulation. So the main measures which are well known in mining industry or any powder industry is a static angle of repose. That's the first one. And the static angle of repose is a natural tendency of the material just to form shape, conical shape, let's say, and we measure it by the angle. And on the left side, just simple shot from the laboratory test with a pipe, which is slightly different than with a funnel, because with the pipe, for example, as I'm interested in simulating a big bunch of regoliths, several kilograms, it can be different. For example, if I use ratio of the filling of the pipe, which is high of 1 diameter or 2 diameters, so the shape after I put the pipe up is slightly different. The second one is dynamic angle of repose, which is more dedicated to dynamic processes, so like rolling, milling, something which is more dynamic, mixing or something like that. And this is similar, which is the angle, but we are looking for the angle which stabilizes during the dynamic process. So we can say, so we are looking for some equilibrium. However, we have to think over about several, let's say, types of phenomena when we have rolling. Mostly we are targeting slumping and rolling, but we can also have cascading, cataracting, or even centrifuging. So you have to consider what you are targeting. And finally, we are super interested how our material is interacting with the external material. So to have how, if we use some scoop or something like that, what will be the influence, how it's gonna behave. So those three measures we can check, but if we try to validate the simulation, and if we assume that X1 is the filling pipe, X2 is granulometric composition, then we have particle size composition, rolling friction, static friction, and coefficient of restitution. And if we would take only levels of 2, 4 levels, then 5 levels, and 6 levels of combination of those parameters, we'll get 17 over 1,000 of trials. So that's why we're using design of the experiment, screening design, Plackett Barman plan to reduce it to 24 trials. From that trials, at this moment, we got very good model with 88 R², and we have the info that most influence in that combination we have for the factor E, which is particle static friction, A, which is pipe filling, and C, not that big, but still, and C is size composition. And what we do next, of course, we can check how those parameters influence our simulation. On the left side, you can see is the static angle of static of repose, and each of that parameter, how it influences. And we can see that the level of pipe filling, as I said, has the biggest influence, size composition, and particle-to-particle static friction. So what we do now, we have to double-check if what we expect with that model with super accuracy 88. We design another experiment, which is full factorial design with center points, which should give us more information about the relation between those components. And that's something I'm going to do, I believe, in next week. So if you'll be in Colorado School of Mines in, I believe, 2 weeks on the conference, ask me. Maybe I will be able to already give you some information. So what's the course of action? Why we are actually doing this? We calibrate the model. We use the experimental data to have the final validation of the material. To that, we add external friction to have multi-parameter process just to have validated simulation, for example, for excavation, for any interaction, or for handling. If I will feel that I have my model validated, I think that would be the easiest way to try to adjust gravity, no gravity. Of course, later on in the future, it has to be validated. But at this point, the way is to validate as much as possible those models in the end Earth condition, because it's relatively easy in simulation, just switch on, switch off many other phenomena. And what is our application? That is, you can find my talk from the last year here about the sieve, and on the right side, yet not calibrated models for sieving screen rotating in EDM. So that's my purpose. But final goal of that validation is to prepare database of what kind of static friction you need, rolling friction, coefficient of restitution, to have valid model which is dedicated to specific type of simulant. And I'm targeting more like medium, large size simulation and equipment. Thank you.
There's another one. Thank you very much. That was great. Okay, so let's open up the floor to some questions, if there are any in the audience. I can't see any at the minute. No? Anybody? All right. Well, it seems like you've explained it very clearly. Thank you. I think that's very interesting. Having a database of all of those different coefficients and relevant parameters for DEM, I think is going to be very revolutionary for anybody that's doing this type of modeling in this field. So thank you very much for doing that. It's very interesting. Cheers. All right. So our next speaker is Kunal Kulkarni from DLR, who will be presenting on targeted mineral beneficiation of lunar regolith, feasibility assessments, and next steps. So please.
So, good afternoon, everyone. My name is Kunal, and I'm representing the DLR Institute of Space Systems in Bremen. And today I will talk about my PhD research topic of targeted mineral beneficiation of lunar regolith, and more specifically the feasibility assessment and next steps part of it. Before we go forward, I would like to introduce briefly what is beneficiation. This is one of the few rooms where I don't think I have to explain too much, but I will give a brief introduction. It's basically a pre-processing step for preparing specific feedstock composition that would enhance the efficiency of the downstream processes for extraction. A prime example would be copper mining on Earth, which also relies heavily on different kinds of pre-processing steps to get more efficiency and therefore more performance from the system. Now, targeted mineral beneficiation, why is it necessary for regolith? Now, I will use the reference composition from the LMS1 regolith simulant. However, the ideas are also applicable for other simulants and obviously the lunar regolith. It's composed of these primary rock-forming minerals, which you have probably also all looked at some point. And they are present in different forms of particle sizes, different proportions, and different linkages in a bulk material that forms the lunar regolith that we would end up excavating. Now, what ideally targeted mineral beneficiation should do is we take the regolith, we perform some magic beneficiation, and we end up with perfectly pure output minerals. However, that's not, unfortunately, how it works. It's much more complicated given the complex composition of the regolith itself. Therefore, multiple stages, sequentially, one after the other, refining the regolith is one of the best ways proposed for achieving more specific compositions for the feedstock. Now here I have on the right side the photo from the beneficiation testbed that we have in Bremen. This was developed in the beginning focusing mostly on ilmenite enrichment, and now we focus more also on the other aspects, other minerals basically. Starting from the top, quickly give you a brief overview of the testbed. On the right we have beginning from the top, a feeder, a vibratory feeder that controls the feed rate of the regolith in the system. Then followed by that, we have a vibratory sifter that sieves the regolith, and the coarse particle fraction is removed from the particle stream, allowing for the finer fraction to fall down to the magnetic separator. Here we have a rotating permanent magnet drum separator that separates the magnetic fraction from the non-magnetic, or rather less magnetic particle fraction. The magnetic fraction is collected separately, allowing for the non-magnetics to be transferred to a turbocharger, which has a spiral electrode inside that, by the virtue of triboelectric effects, produces different levels of charge on different particles, and this is allowed to fall through a parallel plate separator at the bottom. With the parallel plates, high electrostatic fields is applied across the plates, allowing for segregation of particles through the plate while falling down into the different collection bins at the bottom. Now, before I move on to the results, I want to emphasize that what I want to do today is give you a qualitative understanding of how the beneficiation process works, and I do not want to bombard you with 20 different graphs of the different minerals. So the results you're about to see will be averaged across the different results of different experiments, which is comprising of up to 75 samples across different feed rates. Now we start with the mass distribution of the particles through the process chain. We always maintain the input material feed of 300 grams. The simulants are always dried for 2 days before we perform the experiments. And every experiment is performed 3 times to have a better offset for any deviations. Followed after the sieve, which was at the time set for 200 microns for ilmenite, we get rid of almost half of the material in the coarse fraction. And followed by that, the finer fraction is processed with the magnetic separation, which leaves another 10% of the material in the magnetic sections. And finally, we get the electrostatic outputs in the bins at the bottom. So the understanding is that we have at least 4 different outputs from this beneficiation testbed. And it's very important to understand how the mineral trajectory works through all of these processes. As you can already know, mineral characterization of regolith can be quite complex. We use XRD for this method, and we are collaborating with the University in Bremen to do this characterization. However, given that the characterization of the entire system samples is quite resource intensive, we had to limit ourselves to the magnetic beneficiation stage for characterization for all the samples. Now, upon characterization, we always start with the 300-gram samples. After sieving, we observe increase in basaltic and pyroxene-based minerals in the coarser particle fraction, with the rest of it being sent forward to the magnetic beneficiation stage. In the magnetic output, we also observe predominantly more basalt and a bit of pyroxene, while the non-magnetic output is predominant with a bit increase with pyroxene and olivine mineral samples. To look at it more brief, completely an overview, I would like to take your focus on pyroxene and olivine. These are the minerals that were more predominantly collected in the non-magnetic outputs of the system. The numbers might seem a bit low, but again, it's more of an average of the whole system. And we believe with electrostatic results and characterization of those results, we will have change in all understanding of how the rest of the system deviates the rest of the system influences the beneficiation characteristics of processes. Now, in conclusion, what is the understanding? With magnetic beneficiation, we could effectively sort the minerals based on their intrinsic properties, intrinsic magnetic properties, and we could validate with our experiments that in a bulk regolith mix, we can separate or shift the trajectories of the minerals based on their intrinsic properties, which can be a bit tricky when you think of scaling up the entire system for tons of regolith that a lot of the ESRU plants want to aim at. And in general, the analysis supports a good potential for multi-stage beneficiation, which is why we are also currently working on updating our results and building a new system based on what we learned from this one. And that's about it. I wanted to have the QR code for the paper that we're working on to give you more details of the results, but it's still in the process, so you can follow me on LinkedIn, and then you'll probably get to know updates about the paper. Thank you.
Thank you very much. Now I'd like to open the floor to questions. Anybody? Yes.
Well, thank you, Jun Shimada from JAXA. And I have a question regarding scalability. Do you have any upper limits for the flow rate for beneficiation?
So currently, we also tested with increased quantities of 1 kilograms in one of the experiments to process 1 kilograms together. For now, the bottleneck seems to be the turbocharger, which we kind of keep static and allow the material to fall through it with the gravity. However, with the scaling of the system, maybe with multiple systems, it could be a solution for scaling up, yes.
Okay, thank you.
Yeah.
Any other questions? Yes, Clive.
Thank you. The initial separation is gravity, 1/6 gravity from down here. Maybe that, have you thought about that being the bottleneck to get separation going in this system if you take it up to the moon?
Very good point. For the lab setup, we stayed with the laboratory sieve to save some time and get some industrial solutions for now. But we are working on different particle size separators because of the obvious problems of gravitational beneficiation not being as effective as it is here. But yes, thanks for the point.
Thank you.
Any other questions? Yes, at the back.
Maybe 2 questions. Can you comment on why are you getting an increase of basalts in your particle size separator fraction? Is that a problem or a property of the particular simulant that you use, or LMS1, I believe? And also, why are you getting so much orthosite on the magnetic bin? Maybe if you can comment on those.
Yeah, so for the first point, I think it's a property of the simulant itself that there is a larger particle fraction of basalt. But we also tested with 2 other simulants, and we have similar results with those. So I believe it can be both ways. And for the anorthosite, the tricky part was for characterizing the anorthosite. There's 7 mineral phases within the anorthosite, and some of them seem to be more magnetic for some reason. And this can also be, this is only seen with LMS. It is not seen with the other simulants. So our understanding is it's mostly a source of material limitation.
Any further questions? I have a question. How do you optimize this? Or have you done any optimization?
As you can see, there's so many parameters to optimize. It gets a bit tricky. We did some optimization for ilmenite by changing the rotational speeds of the magnetic beneficiation, changing the voltages for the electrostatic field, and by changing the feed rate of the system. And that did lead us to some improvement in results. However, the complete optimization will be quite a tricky part, given the multiple parameters in the system.
Fair enough. Great. If there are no further questions, perfect. So thank our speaker once more.
Thank you.
So our next speaker that I'd like to welcome to the stage is Serena Pirrone from ESRIC, who will be talking to us about how does penetration performance of soil burrowing probes depend on tip design. So without any further ado.
Hi everyone, I'm Serena Pirrone. I work as postdoc at ESRIC, which I recently joined, but today I will show you something related to my PhD work, which was done at the Italian Institute of Technology in the context of an ERC consolidator grant and in collaboration with the robotics section of ESA and the 3SR lab of Grenoble University. So in particular, we investigated how penetration performance of soil burrowers depend on the tip design. To give you a bit of background, it's important to keep in mind that current soil penetration technologies present several disadvantages because they use energy-demanding tools, invasive processes, and require a high level of human support. Particular challenges in this context are the reduction of stress exercised on the system, providing steerability and ensuring safety for the system as well as for the environment where it operates. In this context, robotics, and specifically biosphere robotics, is being widely used for geotechnical engineering applications. And in the lab where I was working, we were looking at plant roots for developing performant robotic burrowers because they have peculiar features which allow them to easily penetrate into soil. For instance, they move by growing at the tip, they exploit radial expansion to penetrate the hardest media, and they have a particular tip morphology. All these things become very interesting if we want to develop technologies for soil exploration. Therefore, in this context, we investigated the tip design effect by executing penetration tests in chambers filled with Houston sand. Houston sand is a terrestrial medium well characterized in terms of geomechanical properties. That's why we use it as a sort of reference medium. We executed penetration tests using two probes differing in tip geometry. One is the conical shape, which is the traditional one of penetrometers. The other one is what we call root-like tip, because it was designed based on the morphology analysis of a plant root. We executed penetration tests in chambers varying in soil compaction level, and we were able to set these by air privation technique using the following protocol in order to obtain samples with a relative density ranging between 26% to 87%, and therefore cover a wide range of densities. Experimentally, we obtained the following outcomes. As you can see here, we found that the biosphere tip is quite advantageous for penetrating into the soil because it implies lower pressure requirements with respect to the conical one. And this was observed for all soil compaction levels and during the whole duration of the penetration process. Therefore, at this point, we wanted to extend this evaluation numerically. Reason why, using the open source software YADE, we developed a three-dimensional discrete element model, simulating penetration of a probe into simulated packing with geomechanical properties of Houston sand. We considered the probe moving by being pushed from the top, which was modeled through addition of new material. And we considered about 170,000 heterogeneously sized spherical particles with rolling resistance in order to approximate realistic particle shapes. To model the interparticle and probe soil interaction, we used an elastic, perfectly plastic contact model with refriction and rolling resistance. This is what our DM simulation environment looks like using YADE. You can see both 3D view and top view on the left, as well as conical tip and biosphere tip implementation. It's important to mention here that we did not include a gravity effect in these simulations for complexity, and therefore we decided to work with a confined state and apply a vertical stress representative of the soil depth we wanted to simulate. Numerical outcomes show a pressure drop associated to the use of a biosphere tip, consistently with what observed experimentally, as experimentally this outcome was found for all soil compaction cases. Since we did not include gravity, of course we obtain penetration pressure curves that fluctuate around steady state values rather than increasing, as observed experimentally. And therefore, if we want to compare modeling to experimental results, we need to compare such steady state pressures to what measured at the corresponding depth, which in our case was set to be about 75 millimeters. As you can see, here modeling estimations work quite well for loose and medium dense soil, whereas some discrepancy is found at the densest soil condition. And we attributed this to the action of some soil chamber bottom border effect on our measurements, as suggested by the pressure curve, which is increasing, meanwhile including some non-linear components. At this point, we were interested in investigating the same process in different media, reason why we executed experimental campaigns at the robotics and automation section of ESA, including penetration tests of the two probes in lunar and Martian regolith simulants, LHS-1 and MGS-1. As done for host and sand, here we consider different compaction levels for both media in order to verify how the initial soil porosity affects the outcomes. For LHS-1, we obtained the following experimental results. As for host and sand, we found out that the biosphere tip implies lower penetration pressure to successfully move into all soil conditions, and this variation is maintained during the whole penetration process, and it's about 30% on average. Then, with the due assumptions, we were able to calibrate our numerical model to simulate the behavior of this simulant. And our modeling results show, once again, advantages in using a biosphere tip in terms of actuation system requirements over the conical one. When comparing numerical versus experimental results, we found a very good correlation for loose and medium dense soil, and still a discrepancy at densest soil conditions due to the action of border effects on our measurements. Here it's also important to consider that this discrepancy is higher than what observed for host and sand, and this may be due to the fact that this soil has a wider particle size range than the host and sand. For the Martian regolith simulant, we obtained similar outcomes, showing once again advantages in implementing a biosphere design. And if we do want also to compare how all this soil behave in a given relative density conditions, we can look at this graph where we are considering medium dense compaction level. And as you can see, for both tips, we found that the Martian regolith simulant is behaving quite similarly to the host and sand, whereas the LHS-1 simulant is much harder to penetrate. Therefore, summing up, with this study we show that implementing technologies with a biosphere tip can be strongly advantageous for penetrating into soil because it requires lower penetration pressure requirements, and this was found across different soils and for each soil across different compaction levels. Experimentally, a pressure decrease of about 25% can be associated to the use of a biosphere tip across all soil types. In terms of pressure reduction, modeling versus experimental results are in stronger agreement for host and sand, and this is due to an advanced calibration of our DEM model because we know very well the mechanical properties of this soil. Despite differences, also for the simulants, we found modeling results that correctly reproduce how the pressure variation depends on the initial density condition. And therefore, we understand that a proper mechanical characterization of this soil is useful to lead to improved quality of numerical prediction in this context, and therefore empower DEM simulation, a supporting tool for the development of technologies for soil exploration. Thank you very much for listening.
Thank you very much. That was very, very interesting. Questions, please. Yes.
Thank you so much, Serena. I agree, it was a very interesting talk. I have a question to your protocols for producing these bulk solids. You were using a beaker, I saw, and then you had different compression levels in your powders. How did you come to these compression levels? Like, how did you fill the beaker?
Thank you very much for your question. So here what we did was using a technique that is well known in geomechanics, which is called air pluviation techniques. It basically consists of pluviating your soil using a given setup. So as you can see, we have a given drop peak height, funnel aperture, and pluviation rate. And by varying these parameters, you can basically vary the relative density of your soil packing. And this was enough for the Houston sand, whereas for the simulants, it was the same, but in all cases except the densest one, where we used first this protocol and then we added some slight vibration in order to achieve 87% relative density for those soils. Vibration for a couple of minutes.
Okay, so just to understand this right, you had a gas stream of air going through it at the bottom? No.
No. I didn't have anything. It was just a funnel with a given aperture size and set at a given dropping height. And by simply varying these parameters, of course, you vary the rate. Mm-hmm. And pouring the soil, you're able to obtain many different compaction levels for your soil samples. This was done manually. So it was repeated many times, but this protocol works quite well and it's quite consistent.
Okay, I would like to talk to you about this later because in our lab we use a powderiometer that also has a similar setup, but there you can also reach very loose compactions by streaming air through the bed, and also you would do a compression from the top, and so on and so on.
Yes, we can talk about it, but I would like to point out that we use this technique because it's useful to get, let's say, properties that are locally constant along your sample. So that's why we went on with this, but we can talk about it more later. Thank you.
Thank you. Other questions? Clive.
Looking at your relative densities you've got there, if you look at the lunar regolith, the top 20 centimeters is a bit fluffy, it gets blown away. And underneath each one of the Apollo landers, there is no blast crater from the engine because everything is greater than 90% relative density. They're interlocking particles. And your penetrator that is going in, that was the model for the heat flow probe that went on the InSight mission to Mars, and it couldn't penetrate Martian regolith the way it was designed. It certainly wouldn't penetrate lunar regoliths. So trying to achieve greater than 87% to test these in simulant is something that I would urge you to look at, because penetrators for the moon, there's very little pore space in that very densely packed layer. And also check out the cone penetrometer data from Apollo 16, because they give you great density profiles in the regolith and they can be mimicked.
Absolutely. Thank you for the suggestion. Indeed, we plan to investigate this further. It was already quite a lot of work to get here, but a lot of follow-up work can be done, so we'll consider higher values if possible to be obtained in the lab.
Yeah, and if it was easy, everybody would be doing it. So
indeed, I agree.
Keep going.
Thank you.
Any other questions? I have a question. So the bio-inspired design was from a root tip. Are all root tips the same? Are there different types of root tips? Like, is there a way to, explore different options, or is there something better?
This is a very nice question. Well, we considered the morphology analysis of a zeamite root, and this was based on a previous work that was done in the lab where I went there, and since I'm an aerospace engineer, I'm not a biologist, I just trusted that. but I think that they all work quite similarly. Their main advantage is the fact that they grow from the tip, and therefore this has a lot of advantages in terms of friction with the surrounding environment. And also in a previous work, which is already published actually in Acta Geotechnica Journal, we also show that the fact that they expand radially is a very key aspect for penetrating in the hardest media, and therefore they are quite excellent explorers. There is a lot of work going on about plant roots-inspired technologies, so we'll see.
Very cool. Thank you very much.
Thanks.
All right, if there's no further questions. Oh, there is a further question. There you go.
Hi, great speak, by the way. 117,000 particles, that's a lot. So what was the contact law you used, and why did you use that one?
Sorry?
What was the contact law for the DM model
Okay.
that you used, and why?
Where is it? Oh yeah, 1 second. Okay, so yes, it's a lot of particles, and that's why DM simulations are extremely expensive computationally, and therefore they solve, let's say, sort of overcome this issue by scaling up particle size, which introduce, of course, some drawbacks in the model's accuracy. But here it was, let's say, fundamental to use this amount. And we used an elastic, perfectly plastic contact model with dry friction and rolling resistance based on a previous model calibration for Houston sand. And it worked quite well, and therefore we were satisfied with this model, and we just proceeded.
Okay, just another question.
Yes.
How much time did you take to make just one simulation?
Okay, so when we talk about simulations, of course, they're not all the same. In DM simulations, very, very important is the relative dimensions between the chamber sides to probe sides and probe sides to soil median particle sides. So as you can see, I reported down the values that we used, and these were found after a sensitivity analysis executed on these parameters. And so with this given specific setup and with this given specific soil, we were able to carry on simulations between, let's say, 1 day duration and 2 days duration based on the compaction level of the soil. Because, of course, when you simulate densest media, simulations are longer because the soil preparation takes longer. So this is the time range, 1 to 2 days.
Okay, thank you.
Thanks.
Great. If there are no other questions, then let's thank Serena once more.
Thank you.
We've made some excellent time this morning, so we're on to our final speaker, Vibha Levin Prabhu from ESRIC, who will be talking to us about microwave vacuum sintering of LMS1 at different temperatures for lunar construction. So.
Thank you very much, Joshua. Hello all. As part of my postdoc research at ESRIC, my work focuses on microwave vacuum sintering of lunar regolith simulants for enabling lunar construction. And today I'm presenting the results on same, showing the work done on LMS1 at different temperatures. So to begin with, I would like to highlight first the applications that we're aiming to target. We're aiming to build porous as well as denser structures for enabling lunar construction. Porous structures such as consolidated and shaped pellets for molten salt electrolysis, for extraction of oxygen and metals, and thermally insulating and impact-resistant structural materials. Both of these require high porosity. On the other hand, we want to also build denser structures which would support building launching and landing pads on the moon, which require high density and high strength. So to make structures large like these with different critical porosity and different critical properties of high porosity and high density, we have to demonstrate the experiments at lab scale, and that's where we are. So we are trying to fundamentally understand the microwave behavior of lunar soil simulants, attempting to manage powder handling in vacuum, and looking at different sintering parameters to overall evaluate the process. So this is our microwave heating device in the lab. It's a single mode cavity design, operates at 2.45 gigahertz with a maximum power output of 900 watt. It is vacuum and inert environment capable and has a temperature control system. The cavity is shown over there, the sample goes inside. And this is the schematic of how it looks inside the cavity. So we have a silicon carbide tube with lids made of silicon carbide as well, both top and bottom. The sample goes inside the tube, and this is sitting on a thermally insulating block in the cavity. Microwaves are transmitted from the side of the cavity. In the side view, you can see there's an infrared parameter which senses the temperature of the tube. So this is a sensor which would be looking at the tube temperature, and it is not directly looking at the sample. So the temperatures mentioned hereafter are tube temperatures. Here I would like to highlight a point that this is a single mode cavity design, so the incident and reflected microwave makes a standing wave in the cavity, and the position in the center is the place where it has maximum electromagnetic field, and that's where we place our sample. So before I get into experimental results, I would like to show you how our research advanced to the stage where we are. It helped us, the challenges we faced along the way, it helped us refine our methodology and improve the quality of the product. So when it comes to microwave, the feedstock has to be a microwave absorber. In our case, we used LMS1, the Mare Regolith simulant, which has a particle size less than 1 mm. It is a good absorber of microwave, but it poses great difficulty in controlling the temperature because of thermal runaway, and that is why we used silicon carbide as a susceptor to assist and bring some control of temperature. When it comes to vacuum with powder handling, it's a challenge. So for managing that, we did two types of things. So the first one was to desiccate the sample overnight, and the second one, while heating the sample, we tried to hold it at different temperatures to slowly and steadily release the interstitial air and the volatile species at higher temperature. Sintering poses its own challenges. With our own GSC measurements, we found out that LMS1, the melting curve, starts at around 1070 degrees Celsius, and the liquidus is around 1300 degrees Celsius. To manage sintering, which is densifying of a powder material below its liquidus, is very critical to be precise in temperature control. And for that, higher heating rates were having a lot of issues, so we lowered the heating rates and brought a certain level of control in the temperature. With this understanding and experience, we designed a multi-step temperature profile to slowly heating the sample to release the volatiles and progressing to the target temperature. I would like to show you a video here of how the heating occurs inside the cavity. You are not able to see the bottom lid here, but what you're seeing is the tube and the top lid. And this is at a tube temperature of 960 degrees Celsius. You can see that the melted phase is bubbling out, and that is indicated by the lifting of the top lid and tilting of the tube. So this is to show you that the process is really challenging. With the control, we could then design two sets of experiments. We have first heated it up to 960 degrees Celsius of tube temperature at 10 degrees Celsius per minute and held it there for 7 minutes. You can see this is the multi-step temperature profile. We held it at 600 and 800 degrees Celsius for 10 minutes to get control of the release of volatiles. This was performed at a power of around 360 watt, and we got well-sintered samples. We went on to then, at a lower temperature of 930 degrees Celsius at the same rate of 10 degrees Celsius per minute and holding it for 20 minutes. The power consumed here was a little less because it's at a lower temperature, but here also we got well-sintered samples. So we did achieve sintering, but when we tried to look at both of our samples, we could visually observe that it has been heated non-uniformly. So when we looked further into the heating process during the whole microwave heating, we could see that in the cavity itself, there's a temperature gradient that forms on the sample, and that is what is reflected in our final product. So we have a low temperature zone and a high temperature zone. Further, when we looked, we could see that the high temperature zone is the one which is facing the direction of the incident microwave. So it is the unidirectional effect of the incident microwave which has brought in the heterogeneity in the sample, and thus it is quite non-uniform. So to look further, we cut the sections and looked at under SEM. So the microstructure revealed that the sample has undergone liquid phase sintering with a low temperature and a high temperature zone. In the low temperature, in both the samples on the left, we can see that there are elongated, interconnected pores, but discontinuous grain structure. On the right, which is a high temperature zone, we can see more continuous grain structure, but large closed pores. These large closed macropores are a result of rapid release of volatiles, and this is a very common phenomena observed in any kind of heating when it is done under vacuum and at high temperatures. So when we looked closer to these samples, for the first sample, we looked at the areas from these different zones, from the low temperature zone and the high temperature zone. We could easily identify the reduction in the pore space from low to high, indicating densification occurring in the high temperature zones. And when we did it under EDS mapping, we could, of course, identify the various minerals that we have in the lunar regolith simulant, but we could also identify the melt percentage, which you're seeing here in the green neon color, which helped us identify the low temperature and the high temperature zones. Similar observations were made for the second sample: low temperature to high temperature, pore space decreasing, melt percentage increasing. So with this, we of course understand that we could form a sintered product, but it has undergone non-uniform heating. So I could not assess very properly the compressive strength or impact strength, the bulk properties of the sample, but I went on to do some hardness testing. We used the Vickers hardness testing machine, which uses a square-based pyramid indenter and makes an indents at given loads, and the size of the indentation indicates the hardness of the material. So we picked up, again, the zones from low temperature and high temperature. We could easily see that the low temperature showed large indentations, quite a few large indentations, and the high temperature had very small and clear indentations, indicating that that zone has higher hardness than this zone. So at this stage, it is difficult to assess the behavior of different temperatures on the quality of the final product, but it definitely helps in identifying some key parameters. Susceptor-assisted microwave sintering is certainly effective in vacuum, and it can produce variable porosities through liquid phase sintering. So we are able to achieve different porosity sample, which kind of goes back to what we are trying to achieve for different applications. We could also address the simulant degassing by multi-step temperature profiles, and we expect fewer issues on lunar conditions. And now the focus is on optimizing the susceptor geometry, the microwave irradiation, and thermal insulation to control the uniformity of temperature and porosity and hardness of the final product. Thank you very much for your attention.
Thank you, Vibha. That was great. All right, questions. Wow, lots. All right, we'll go left to right this time. So I think, is that over in the corner? Jerry.
Good work as always. So the benefit of microwaves is the penetration aspect, yes. Because regolith itself is extremely poor thermal conductor. That said, do you think you might think about going back and forth between having a different, heating mechanism that is more uniform, at least from the outside, and working inwards, versus trying to adapt at least this a single microwave horn to do the sintering instead, maybe bringing in different horns to cover that whole area?
Yes, thank you so much for that question. That's where we are heading. We are definitely heading to irradiate it from different directions because we could see the unidirectional effect. And yes, it will always keep on going back and forth because the thermal conductivity of the simulant and the microwave absorption of the regolith or simulant has to be balanced somewhere.
So you can pulse the microwaves just like, defrosting, a chicken or something like that to try to make sure that there's a resonance of that heating so you don't overmelt one location or another.
The localized heating.
And I think I mentioned this last year, the Koreans have done a tremendous amount of work on microwave sintering of regolith with multiple directions.
Yeah. Thank you so much.
Yes, in the middle.
Thank you, Vibha. I was very interested in why you're choosing this approach. So basically, you create a silicon carbide heating element, and you excite this with microwaves. Can you talk a little bit about the, what the yield is, like how much electrical current you need to do that as compared to just putting electricity right into the silicon carbide, which is the way we do industrial sintering all along. So your approach is to have like a mold as a heating element, and it's very direct, so it's very inhomogeneous because of the microwaves not being homogeneously distributed. But my take is that you lose at least 20 to 40% electrical efficiency doing that. It would be much more efficient to just straight away put the current in the silicon carbide and more homogeneous, because these silicon carbide heat elements, they have a homogeneous energy excitation until 1,600 degree, but the microwaves, they level off at 1,200 degree, which is exactly the range you want to work in. So I think you should really look at that. Like this indirect way of microwave sintering, I don't think I agree with that. I don't know, I'm serious. I don't think this is a path to take, because many people have talked and worked on lunar regolith microwave sintering, but the whole point is doing it directly.
Yeah, that's right. But I think when we come to sintering and trying to bring the control of temperature, it's there where we need susceptors. We can certainly use microwave, and I think a lot of people are aiming at melting the regolith directly with microwave, which is much easier to do. But when we want to do sintering, we have to introduce these susceptors to bring the control. But that said, of course, I would be now proceeding to do test some more other methods of sintering, like compare it where we are, as you said, like to see the efficiency, how this stands with other modes of sintering, and then maybe give you a better answer of why should we definitely go for susceptor-assisted microwave sintering. Because it would also depend upon different areas of the moon. It would also depend upon the type of simulant you choose, because Mare would behave different, Highland would behave different, and it is possible. I'm showing you right now using a silicon carbide tube, but it is possible that some of the minerals that are present in the lunar regolith could actually act as a susceptor. And if we could mine them on the moon and add it at different locations on the moon, we may prove that this method would prove to be more efficient than other methods. So it's an ongoing research, and I would certainly be comparing it with other technologies and then probably give you a better answer next time.
Thank you so much. Make sure you really do a very well beneficiation to have very homogeneous particle sizes and so on and so on.
Yeah,
thank you.
Thank you.
Further questions in the middle?
Thank you very much. Interesting work. I think what you just said is a nice transition to my question. There's been some work in Albi in France about looking at the impact of the amorphous content in the simulant on laser melting. I think it could be interesting for your case as well to look at the impact of the amorphous content, which might help also the homogeneity of the microwave sintering. And I'm thinking then, could you do some experiments on remelting a sample that you have already sintered? Because then what you seem to have from your picture is a composite with an amorphous matrix with particles inside. So that could be interesting to look at a second pass of the microwave sintering on that.
Sure. Thank you. Thank you so much for that suggestion.
Further questions? Yes.
Thank you. Well, could you elaborate a little bit more the shape and the size of susceptor? It has to be a plate, or it could be like a beans?
Yes, that's what was my final remark, that I would be working with susceptor geometries, different geometries, to see if the improvement, and certainly improvement can be made with working with different geometries of susceptor. A plate type or a beads, or it could be in some form we place it in between the sample. So yes, this is all the research that has to go from here. So yeah.
Okay, I see. Thank you.
Clive.
Thank you. It's a very nice talk. 2 comments and a question. That when you go to lunar regolith, the maturity of the regolith is critical. Yeah. When you get nanophase ion in mature regolith, it's going to combine with those microwaves much better from immature. You're dealing with immature regolith. So the other thing is that, and I've forgotten what the other comment was, but I'll come back to it. But the question I have, why don't you just rotate the stage rather than...
Going to do that next.
Okay, okay. So, because I was just... And, oh, I know what the other comment was. It comes back to getting these results throughout this session today, apart from the modeling sessions. But when you're doing experiments, it comes back to X-ray computer tomography of those samples to truly get a 3D picture of what the product is and a very, then you can get a quantitative measure of porosity heterogeneity across that. With a thin section, you get a slice. And I think start bringing in that analytical technique to your experimental charges is really going to open up the trade space for how you then adjust your experiments. And I think you'll make progress a lot quicker that way.
Yep, thank you. Thank you so much for that suggestion.
Any other questions? No? I have a question. So you used LMS because it's more susceptible to microwaves. What is the relative contributions of the sort of susceptor contributing to the heating versus the LMS in and of itself? Like if you were to swap it out for LHS, would you notice a huge difference?
Yeah, so I cannot give you in numbers, but why I chose LMS, as you said, because it's a better absorber of microwave compared to LHS. Majorly, these minerals, like the iron-rich minerals, they are the ones which absorb the microwave so well, and that is why we see LMS absorbing it better than LHS. So I have not made the exact calculation for how much comes from the susceptor or how much is LMS alone, but it's the minerals which are absorbing the microwaves better. And they are the ones which are rich in iron and magnesium. So mostly pyroxene, olivine. I can also say the glass, but for glass, when we say amorphous phase or glass, we have to really understand the content of that glass. And in that, if there is a higher percentage of iron, yes, that amorphous phase will be a better absorber. So I have to go down to that level and then bring some numbers.
Very interesting. Thank you very much. So if there's no further questions, then that was the last talk of today. So let's thank Vibha once more. And because we had one of our speakers drop out or speak yesterday instead, we're actually finished for the morning. So thank you so much for all of your attention. Hopefully you learned something very interesting in this talk today, or in these talks today. I certainly did. So you're free for the afternoon. Enjoy lunch, and we'll see you back later on. Thank you.